The Nelson model more accurately models the diurnal and seasonal dead fuel moistures using hourly fire weather observations. So it doesn't, the good thing about it is it doesn't require any human input. So now, once we get this system fully implemented, and with the changes to the live fuel moisture model, it will run every day, essentially unattended, automatic. And it can be run on things like grids, which has never been able to do before. So, but the cool thing here is that we did a lot of testing implementing it both in WIMS and running it for a long time operationally, because it's computationally it takes more time, even though in the end all it does is produce the same numbers: 1 hour, 10 hour, 100 hour, and 1,000 hour fuel moistures from the same model. But it's also been integrated into all the fire behavior prediction tools. So it's a way for us to align something that to where we're using the same model in all our tools, whether it's for Farsight, Flam Map, or for NFDRS, all using the same thing, which is a very good thing. The simplest way to think about this is that that in the Nelson model we create sticks of any size that we want. And if we go in and tell the Nelson model to create a little tiny stick and to force the weather conditions around that tiny stick based on these 4 weather observations: temperature, relative humidity, solar radiation, and precipitation, the model does the rest. So essentially for NFDRS, we align this with what we did before. We have 4 dead size classes of fuels. They all represent time lags of 1, 10, 100, and 1,000 hour. And we create sticks of associated, basically, diameters that represent those fuels that we always used before. So in this case, we define 4 sticks, one with a 0.16 inch diameter, 0.5, 1.6, and 3 inch diameter, and we allow the model to do the rest. The model is a fully physically based model, so it looks at the moisture transport from the outside surface of the fuel to the middle and back. And it does that not just every hour, but multiple times within the hour. So for a typical fine dead fuel in our 0.16 inch class here, it can do as many as 135 diffusion calculations for 1 hour for that one stick. But all that's covered in the model itself, and the only thing you really got to know is we create sticks of different sizes. We give it all the same, essentially, forcing conditions around the outside of the fuel, and we let the fuel figure out what its moisture content is. We let the model figure that out for us. We also have a snow flag, which defines a special set of conditions when fuels get buried under snow. Because we know things like they're going to be pretty close to freezing. We know they're going to be shaded from solar radiation. They're also going to be shaded from precipitation. And they're going to be in a really humid environment. But turning it on and off, I don't think is all that necessary, because the model will do the moisture content fluctuations just fine. It's really about encouraging that kind of fuel recovery over the winter period that doesn't always happen if you don't include the snow flag. And I will tell you that our intention in the very, very short order is to provide guidance about snow flag conditions from grids, because it's kind of silly for people to have to go in and turn snow on and off when we're modeling snow cover across the entire continent. So we can do it pretty well, and it's good enough for these fire danger applications. So we already have the wheels in motion to create a way to automatically pre-populate this snow flag, so it's turning it on and off as the snow cover progresses or recedes. And so that should help too. Yeah. Like, so we've been using the National Snow Data Assimilation System, looking at basically some of their gridded snow products on a kind of 2.5 kilometer resolution or less. And we also have another system we'll talk about tomorrow for topo fire, which is doing it at using the water balance at 250 meter so we can actually sample all the RAWS stations and provide a first guidance, and it can be overridden locally if you have a good reason to do that, but really we need to get away from so much of this, if a human doesn't go in and put in the snow flag or turn the snow flag off, the system doesn't work. And we've eliminated everything except snow flag in this new system, so that's our last piece. So this Nelson model's got some really handy features. It does actually deal with water vapor diffusion through the fuel, both into and out of the fuel. It also deals with capillary water transport, so basically the ability of water to squish inside the cells and move laterally along the fuel itself. Probably the single best thing for us is this idea of deriving a surface energy balance rather than putting in a state of the weather to estimate fuel temperature. It does an energy balance at the surface of the fuel using solar radiation, using measured air temperature, measured relative humidity to actually give us the best estimate of fuel temperature. And that way we don't have human inputs for these fine dead fuel moisture models anymore. It does actually do dew formation, which is pretty cool. So in places where you have nighttime recovery, the old model would have never done that. But when you're doing that surface energy balance, and you can show that surface energy balance, the relative humidity at the surface is approaching, or the temperature is approaching the dew point, it can actually wet the outside of that fuel as a function of dew formation, which is handy. And as I said before, it's scalable to any size. So this is just an example plot from Fire Family Plus of solar radiation for our station in Blue Mountain. But really this solar radiation thing is the key. It's like been the missing link. The energy balance is straightforward. It looks at heat loss through conduction, long wave radiation, evaporation, and then heat gains through solar heating and convective heating. There are some constants in there that make it work, but essentially by using solar radiation and the measured meteorology, we can get at that. As I said before, the model works by looking at how moisture moves from the outside into the fuels as it's either wetting up or drying out, depending on the gradient. So the model always has 11 nodes. One at the center, 9 concentric bands in the middle, and 1 on the surface. So it essentially models the node-to-node moisture transfer, the node-to-node temperature, and the node-to-node saturation of each one of those little tiny parcels. And so again, it deals with other things in addition to the diffusion, like capillary water transport. So basically the idea that you can squish water this way and water moves laterally along the stick itself. But one of the biggest things that I think was that one of the benefits of this model is having a direct precipitation input. The original fine fuel moisture model had 0 rainfall input. The only way that it wet the fuels is by setting the state of the weather to raining. So if the state of the weather wasn't raining at observation time at 1300, then the fuels stayed dry all the time. So with this, basically it says how much rainfall do I capture, and then how much does the moisture change as a function of that captured rainfall. You'll notice that it asymptotes up here, just like the way that we talk about 1,000-hour fuel moisture. Because we don't have rainfall amount into 1,000-hour fuels, right? We have rainfall duration. And the idea is that it's not really the amount of rainfall that wets the fuel, it's how long that rainfall is delivered over. Because the only place that fuel's wet is right around the surface. So you can pour an entire bucket of water on a 1,000-hour fuel, and if you pour it over really fast, what happens? All of it runs off, except for what's stuck to the skin of the fuel itself. That's why the old model uses precip duration as a direct input instead of precip amount, because it was better correlated to the wetting effect of the rainfall. Well, that's kind of embedded in the way this model works, is that there's an asymptote that says above a certain rainfall, above about a 1.5 millimeters of rainfall, additional rainfall has no effect on the moisture content. But rainfall that was delivered at 1 millimeter an hour for several hours would have a different effect. If we look at how it performs over time, we see, so this is for Burnsville, North Carolina, and Mayo, Michigan. This is from Nelson's original paper. You see some really cool things though, and things we've never been able to do with fire danger for sure. And that is the diurnal variation, basically the within day variation in fuel moisture content. So what this is doing is positioning us for the next iteration of NFDRS, which means that we can then go from a once per day observation of fire danger to hourly estimates of fire danger. And those hourly estimates coupled with the wind speed at that hour are going to change a lot about our capabilities in the future. But this model gives us the ability to model the diurnal cycle a lot better than we've ever had before. So if we just look at some examples, so we know from the original NFDRS that fine fuels respond super fast to changes in weather conditions, right? So we call it a 1 hour fuel because it varies basically every hour as the weather changes. And as we go up in time lags, so the 10 hour responds to a longer duration of wetting and drying cycles. So what you see is as you start out with a 1 hour fuel, it's really noisy. And that's because hour to hour, day to day, the weather is changing, and those fuels are responding immediately to changes in weather conditions. As we go up farther to the 10 hour, you start to see those variations dampen. They don't go up as much like they did over here. They're slower, but still very pronounced. If we look at what the 100 hour and 1,000 hour look like, we see that the 100 hour fuel moistures drop down, and their cycles are more like a week. And then if we look at the 1,000 hour, it still looks similar to the 100 hour, but you see a much smoother response. And to be honest, the reason that NFDRS ever worked at all is because of the old 1,000 hour fuel moistures. They're about the only thing that systematically worked everywhere to tell you where you were within a season. And that's what we tried to achieve with the same model and unifying with a straightforward model that can model all these. We did a lot of learning. We do that every day, but this was painful. So NFDRS has been running for about 15 years or so with the Nelson model itself. So 2000, give or take. It got modified in 2006, and the code had been shipped around, shared around, but I don't think anybody ever really looked all that deep, which is kind of sad because we discovered a few things as we were going through the model development. I won't get too deep into them. But what we found, first of all, is that when we ran the uncorrected Nelson 1,000 hour and we looked at a corresponding ERC, we saw some goofy things. One is that it never wet. Like the fuels would essentially never wet, but they would dry out at this steady, systematic rate. And this only applied when the fuels got big. So all the old applications, like the fire behavior applications that only use the 1, 10, or 100 hour fuel moistures out of this system, would have never seen it. So what we see is that it dried out really well, but it never wet back up. And consequently, in this place that was in Nevada, I think actually, is it Utah or Nevada? In Utah. So the Cedar Mountain, what we see in a place that's monsoonal driven, where the fire season should be over in July, the fire season is peaking out here in September. So when we dig around, we find that the rate that the fuels were able to soak up moisture and the rate that they were able to give off moisture were, for large diameter fuels, were off by a factor of about 1,000. So once we realigned that to adsorption, desorption rates that were roughly similar, we get something that's where the entire seasonality shifts by 2 months back towards actually showing up monsoons again, which is a good thing. And then we found something like this also. So we see these, this is a 1,000-hour fuel moisture trace, and if you're used to looking at 1,000-hour fuel moisture traces, they never go up that fast, and they never go down that fast. So we saw these big spikes again. We saw more seasonality, which was good. The big spikes were because the way that the model works is that it's a weighted average based on the volume of each concentric ring. So if you imagine a bunch of concentric donuts, and the outside concentric donut has a big diameter compared to the center, and the same width all the way around. So the volume that it takes up is in some cases 4 or 5 times as much as what's in the middle. When you do a volume weighted average, which is how the model worked, it was disproportionately weighting the outside of the fuel, so that when it rained and wet just the outside of the fuel, you'd get these big giant spikes, and then the next day it would the outside would evaporate off and it would drop right back down, and then so we would get these these crazy peaks. So it turns out all you got to do is stack them up and take a median, and you can go from this boom, 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 to this, which is just looking at the median of all the nodes, and it looks a whole lot like the old 1,000-hour fuel moistures now. So with those 3 things, aligning the stick diameters for each of our 4 classes, looking at how we actually average all the nodes, and then changing the absorption rate, we fixed a lot of things. So the new WIMS, if you haven't been in there very much, go into ENFDR, you have a model manager role, you'll see a screen that looks like this. We have, if you're trying to match your local 1,000-hour sampling program and you have the ability to change these diameters, which you can do, you can actually like almost calibrate against your local measurements if you want to go that far. Because in WIMS, you define the diameter classes, basically the diameters of the fuel, and then you can also turn on the Nelson 100 or turn on the Nelson 1000 or switch back to the old 100 and 1000 if you want to. We left that in there. It's almost an artifact. We referred to it as the full Nelson and the half Nelson. But that's going to go away because there's no point in having that there because we're not going to put it in Fire Family Plus. But essentially, yeah, this is just the code view of what it looks like when we create these fuels. And it's pretty straightforward. We just create a stick and tell it what to do.